So we're going to be looking at gravity, at Isaac Newton's law of universal gravitation. When you hear about the law of gravity, what we're talking about is what Isaac Newton came up with. So you have been taught by me and other physics teachers that objects in free fall on the Earth in a vacuum accelerate at 9.8 meters per second squared. Now we're going to start to ask why. How come? The reason that they accelerate at 9.8 meters per second squared is gravity. More specific, it's because, Justin, the Earth has a gravitational field strength, and the Earth's gravitational field strength is 9.8 newtons per kilogram. Nick, what does newtons measure? What do I measure in newtons? Starts with the letter F. Force. What do I measure in kilograms? Starts with the letter M.
Mass.
So this is really F over M. What is F divided by M? This is another way to write acceleration, but the reason that objects fall at 9.8 meters per second squared is because the Earth pulls on them with a force of 9.8 newtons of force for every kilogram of mass. And you're going to see more and more when we're talking about gravity, I'm going to refer to the acceleration using these units because we're talking about gravity pulling down on it with a force on every kilogram of mass rather than meters per second squared, which are convenient to use when we're talking about distance and time and all that stuff. Up until now, we've been aware of two ways to find this little g, this 9.8. One way we did last year, you remember we did a lab activity in the back stairwell over there where you were dropping an object and timing how long it took to hit the ground, and we were trying to use that to calculate g. Now we were way off because human reaction time, I was happy if you got anything between 5 and 15 meters per second squared. So one way is the gravity field can be determined by measuring the freefall acceleration at that location, and if we had fancy computer timers, we would then say F net equals ma. Who's winning? mg equals ma. The m's would cancel. You get an acceleration exactly g, and we would get that 9.8 bang on with nice fancy schmancy electric eyes and computer timers. In other words, we can drop an object in a vacuum and time its free fall accurately. The second way is by finding the gravity field at a point by measuring the weight, mg, of a small test mass m, and the ratio of the weight in newtons to mass in kilograms gives the gravity field. I'll prove it to you. Look up, I have here a Newton scale. Kimia, you're the close one. This is a 1 kilogram mass. If Earth pulls with 9.8 newtons on every kilogram, when I hang this on my Newton scale, it should be just below 10. It should be about 9.8, yes? Okay, so that's another way that we can calculate the Earth's measure the Earth's gravitational field strength. The Earth's gravitational field strength is 9.8 because of that. Now, here's the problem. When we went to the moon, we needed to know the moon's gravitational field strength before we landed on it. Both of these methods that I've showed you requires you to be there to measure it. How did we figure out the moon's gravitational field strength before we got there? We needed to know because we need to know how strong to build the rockets that were being used in the moon lander. Or when we send probes to Mars, we've never been to Mars, but we know very accurately, Gabe, what Mars's gravitational field strength is. How did we figure that out? We had to know what it was so that we could safely land lunar rovers and things without them crashing. Okay. So, first of all, another way to say acceleration due to gravity is, you've heard me say this phrase, gravitational field strength measured in newtons per kilogram. Another way to write acceleration, so that means it's another way to write meters per second squared, but newtons per kilogram. And here's the question. How can we figure out little g universally? How can we figure out the gravitational field strength of planets that we haven't been on yet? Isaac Newton found that universal gravitational field strength depended on two things. It depended on the mass of the object creating the gravitational field. Mass of the planet, mass of the moon, mass of the star, mass of the black hole, mass of the whatever. By the way, do you all have mass? Yes. You are all sending out gravitational fields. They're just really, 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 really small. I should have done about 20 more reallys. Okay. Really small. So Newton found that it depended on the mass of the object, and he found that it depended on the inverse square of the distance from the center of the planet, or the moon, or the star, or the object. In other words, Isaac Newton found this. If you want to find little g, and I'll put a little subscript, universal, he said it was proportional to, it depended on the mass of the planet divided by the square of how far you were from the center. And since I said the word center, I'll use the letter R. Some textbooks will use the letter D for the distance from the center. I tend to think of it as a R radius because I said the word center. Now, if you look at this, though, Nick, what are the units for mass? What are the units for distance? Meters. This is kilogram per meter squared. I need to get this into newtons per kilogram. We need to multiply by a conversion factor. The same way as you need to multiply Celsius by something to convert it to Fahrenheit. The same way as you need to multiply kilograms by something to convert it to pounds. We need to multiply it by a conversion factor. Here is the universal gravitational field equation. Little g equals big G, big M, over r squared. Did I put that on your formula sheet? Sort of. And I'll explain to you how sort of later on. Now, big M, massive planet or star or moon or whatever. R squared is that. Big G, this is the constant that we have to put into to convert our answers into newtons or newtons per kilogram in this case. And it's small. It's 6.67 times 10 to the negative 11. Its units are newtons meters squared per kilogram squared. It's on your formula sheet. Can you find where it is on your formula sheet in the table of data? Found it, Kimia? What did I call it on your formula sheet? What did I call it? On your formula sheet, I gave it a name. First of all, find where it is. This is also my way of putting people on the spot. Okay, this is the universal gravitational constant. This is the gravitational constant of the universe. Okay. 6.67 times 10 to the negative what? Sorry, times 10 to the negative what? Is that big or is that small? The gravitational constant of the universe is 0.0000000000667. Gravity is an incredibly, incredibly, incredibly weak force. I think it's 10 to the negative 38 times as strong or as weak as the force that holds the atoms together. So it is by far the weakest. Now, Newton predicted that he needed that big G there, but because it was so small, he was unable to measure it. So he always set up his equations so that big G would just cancel. And they did it that way for about 100 years. And then Henry Cavendish actually did an experiment to measure big G in 1798. This is, to physics nerds, the famous Cavendish experiment. Put your pencils down, look up. Once Cavendish got big G, Gabe, the first thing he did, we can calculate the mass of the Earth, finally. I don't know if you ever wondered, Danielle, how do we know what the Earth's mass is? It's not like we put it on a scale. How do we figure it out? Believe it or not, the first methods literally took shovels full of dirt, measured their mass to get an average shovelful of dirt, and then multiplied that by the volume of the Earth, because we assumed it's dirt all the way down, and that was our first estimate. Okay? Cavendish came along and he said, ha! He knew the radius of the Earth. We've known that for about 2,000 years. A Greek mathematician named Eratosthenes used some clever geometry to figure out the radius of the Earth by using the sun's rays and the well and some very clever geometry. We've known that for a long time. So we knew the radius of the Earth, and he had just found big G. So Cavendish wrote this: little g equals big G m over r squared. Danielle, he said, I want to get the big M, the mass. I'll even put an E there for mass of the Earth. I want to get the mass of the Earth by itself, Danielle. How would I do that? By the way, you're going to see often we have two G's, and so you'll hear me say big G and little g, or you can say capital G and lowercase g. I just go big G, little g. Make sure you're careful when you're articulating with me. Danielle, how am I going to get the M by itself? Yeah. So Cavendish did this. He said, oh, it's going to be G r squared divided by big G. Now, little g, we've known, is 9.8. That's the Earth's gravitational field strength. And they knew that they could do experiments to measure that quite accurately even back then. He knew the radius of the Earth, 6.38 times 10 to the 6th, don't forget the squared, divided by 6.67 times 10 to the negative 11. Could you all practice typing that into your calculator, please? Now, Cavendish would have been calculating this by hand. He probably would have taken half an hour or an hour to do this by hand. His heart would have been pounding. His blood would have been racing, because finally he was going to be the first person to actually calculate the mass of the Earth, not guess at the mass of the Earth. Hannah, what'd you get? Times 10 to the? Hannah, can you look on your formula sheet where I have all the data? Is that what we said the mass of the Earth was? And I'm also saying you do need to know that the mass of the Earth is on your formula sheet where I have all the data. And I think the radius of the Earth is there as well, the 6.38 times 10 to the... Okay. Is that what it is? Yeah. And Cavendish went, wow, this number is way too big. This was, Maggie, the first hint that we had that it isn't dirt all the way down. It was the first hint that we believe now that at the center of the Earth, there's a very dense iron core that has more mass than just if it was made of dirt. We have other evidence to suggest that there's an iron core down there. We don't know for sure. It's still a hypothesis. Every picture that you've seen of the Earth that has part of it cut away and shows you that core, you should be aware, Sam, that's a complete hypothesis, because until we drilled all the way down there and go all the way down there. But you know what? That hypothesis explains about 15 different phenomena, so we're pretty sure. But, by the way, have you read in the news recently the North Pole is moving? The magnetic North Pole is moving? That also suggests that there is a very dense semi-liquid iron core down there, and it's moving. Okay. So that's how we can find universal gravitational field strength. Now let's find universal gravitational force in newtons. Turn the page. So we said that gravity is a force that exists between the Earth and masses on its surface. Actually, no. Gravity is a fundamental universal force. It exists between any two masses anywhere in the universe. So right now, Chloe, Danielle is exerting a very slight gravitational force on you and pulling you towards her. Now, it's really 38 reallys small, so you don't notice it. And also, Hannah is about the same distance away as Danielle, and so she would be exerting a gravitational force on you in the opposite direction. So not only is it really small, really all of the ones surrounding you cancel out. The net force is zero, except for the Earth. You with me, okay? Okay. This diagram below shows two masses, big M and little m. You know what? Let's make this the Earth, and let's make this the moon. And let's compare the gravitational force acting on these. Now, it is true that the Earth is reaching out and exerting a gravitational force on the moon, because the Earth has mass. And it is true that the moon is reaching out and exerting a gravitational force on the Earth, because it has mass. Which of the following statements is true? And you know what? We're going to vote. A, the force exerted by the Earth is greater. B, the force exerted by the moon is greater. Or C, they're the same. We're going to vote, or did you going to say? Are you voting already? Are you ready? Are you ready? Are you ready? Who's going to vote for A? The Earth is bigger, of course the force is greater. The Earth is bigger, of course the force is greater. No one. Who's going to say B? C. This is weird because my block A's, almost all of them picked A. C is correct. Why? Oh, boy. What law is that, Hannah? Now, they each exert the same force. Because the moon has a smaller mass, it will have a much bigger circular acceleration. But believe it or not, the Earth moves around a little bit as well. Part of that helps explain tides. Since we have an expression for universal gravitational field strength, little g equals big G, big M over r squared, getting an expression for universal gravitational force is trivial. When I say to you, get the obvious one, what do we always write? More specific, what two letters do we always write? So one way I've told you that we can write the force of gravity is little m, little g. But now I've just told you that universal gravitational field strength is big G, big M over r squared. So I guess universal gravity is little m, big G, big M over r squared. There. Although I gotta be honest, we almost always write it in this order. Big G, big M, little m over r squared. Or sometimes instead of using big M and little m, they'll use M1 and M2, especially if both masses are nearly the same size. But typically if I'm doing a moon orbiting a planet or a satellite orbiting a planet, I'll use big M for the planet and little m for the satellite. Is that formula on your formula sheet in this unit under gravitation? Yeah. So, in the box we have this. The force of gravity is equal to big G, M1, M2 over r squared. Or they may put a D underneath there for distance between the objects squared. Or they may use big M, little m if you're looking at a big planet and comparing it to a tiny orbiting asteroid or something like that. We need to look at some of the math here. Let's pause. I've been ranting at you that gravity is really small. How small? Let's calculate the gravitational force between two 1 kilogram masses separated by 1 meter. So the universal gravitational force, and you know to use it because there's two masses, is big G, M1, M2 over r squared. Who remembers what was big G, the universal gravitational constant, the gravitational constant of the universe? 6.67 times 10 to the negative 11. Mass 1 is 1. Mass 2 is 1. All divided by 1 squared. Please don't reach for your calculator, Danielle. Put your calculator down, Danielle. Danielle, put that calculator away. Danielle, what's 6.67 times 10 to the negative 11 times 1 divided by 1 divided by 1? In your head, please. And now we've converted into a newtons. The force between, if I had another 1 kilogram mass and I held them 1 meter apart, the force between them is 0.0000000000667 newtons. Meh. minuscule. Calculatable. And you saw from the Cavendish experiment, if we up the masses, measurable with some cleverness, but really not very big at all. Okay. Some of you may find, by the way, on your scientific calculator, if you look on the inside cover of your case, you might have some constants inside there. You might find that your calculator has a hotkey for the 6.67 times 10 to negative 11, and it might have a hotkey for the mass of the Earth. If yours has that, and you figure out how to use it, go ahead. It'll save you some typing. What direction does gravity act in then? Towards the center. Towards the center. We had our musical interlude. Let's see if we can expand on that and just do some thinking. Did you all just turn the page? Since you all just turned the page, let's write our universal gravitation formula there. Okay. Oh, but in this case, it says the masses are equal, so I guess instead of writing M1, M2, I could have just written MM. You don't have to, but for what it's worth, it says they're equal. And it wanted me to use a distance D. Okay, I'll write it that way just to show you that it's an easy translation. Now that I've written it that way, I'm going to go back to, I think this is the way I put it on your formula sheet, yes? With an R, I think? Yeah, okay. Our original force is F. What if we double the distance? Will our new force be bigger or smaller? Smaller? How many times? So our new force would be F over 4. 4 times smaller. What if we triple the distance? Sorry? Yeah? 9? Yeah. 9? Yeah. 9, yeah. 9 times smaller. What if we quadruple the distance? By the way, this phenomenon, we call this the inverse square rule. This works in physics for pretty much anything that radiates out. So for example, if you're at a campfire and you feel, if you hold your hands out, how much heat there is on your hands, if you go twice as far away, you'll feel a quarter as much heat. Or if you go back to your original location and you go twice as close, you'll actually be 4 times warmer. That explains why when you go close to a campfire, you can get fairly close pretty casually, no problem. And then all of a sudden there's a very short distance where, oh, I can't hold my hand there anymore. It got way warmer really fast. It's the inverse square rule. What if we double one of the masses? What if we double both of the masses? Okay. What if instead of doubling the distance, what if we cut the distance in half? What if we get twice as close? Will that make it stronger or weaker? How many times? What if we double one mass, double another mass, and then also double the distance? You saying they all just cancel out? Yeah. Okay. Now, gravity is usually minuscule unless one of the masses is huge. A planet, a star, a moon. Even a moon, though, gravity is big-ish. But really, planets and stars and black holes, oh my. If we assume that the mass of the Earth is 5... Sorry, no, we don't have to assume. Cavendish was able to calculate that the mass of the Earth was 5.98 times 10 to the 24th. And we know that the radius is 5.38 times 10 to the 6th. Let's find the gravitational force that the Earth exerts on a 50-kilogram person standing on its surface. Now, technically, I should go radius of the Earth plus the person's height, but the person's height is so small compared to the radius of the Earth that I'm going to ignore that. Let's find the force of gravity. It's going to be big G, big M, little m over r squared. What was big G? 6.67 times 10 to the negative 11. Big M, 5.98 times 10 to the 24th. Little m, 50, divided by 6.38 times 10 to the 6th squared. Yes, Danielle, you can use a calculator this time. Wait a minute, I can do this in my head. Sure I can. 10 to the 11, 10 to the 24th, add a 0, squared. Yeah, and then, yeah. Double check me. Yeah. 490, I think? I think you get like 489.9 something like. Sorry? No, I lied. I didn't do it in my head. I cheated. Here's what I did, Hannah. I used the mg equation from Physics 11, and I went 50 times 9.8 because I said, you know what? If it worked in Physics 11, it should work with the universal equation. And kind of what we've just done, Hannah, is we've done an error check. You know what? Since this gave us the same answer as our old method using the measured 9.8, we can have confidence that this is correct as well. I'm flattered that you thought that I could do that in my head. I fake it pretty good, but I cannot lie about that one. If I do something in my head, I'll always be honest, and I didn't do that one in my head. Well, at least not that way. At the same time, I wasn't pulling out a calculator to do the 1 times table. You caught yourself partway through, I hope. Because I saw you entering numbers. Please tell me you didn't start entering the ones. Please tell me you caught it before that. Okay. A little worried. Okay. What's your homework? Number 1. Put a star next to number 2. It's tough. I'm going to assign it. Number 2 has a potential Nobel Prize in physics hidden inside of it. This is called the 3-body problem. The reason it's called the 3-body problem is there's 3 masses. Okay? What's it asking you to find? The net force on the 500-ton mass. Do me a favor. Can you call the 500-ton mass mass 1? Let's call the 250 mass 2. And let's call the 1200 mass 3. Chloe, what does it want us to find the net force on? Which is mass number? Here's what you're going to do. You're going to find the force on mass 1 from mass 2, magnitude and direction. You're going to find the force on mass 1 from mass 3, magnitude and direction. And you'll add them vectorially. And by add them vectorially, if they're in the same direction, just add them. If they're in opposite direction, winner minus loser. We don't know of a way to do this in one step. If you can figure out a way to do this in one step, you will have solved the 3-body problem. So, for example, when we look at our solar system, which has the sun and 8 major planets, there's 9 bodies involved. Right now, when we're doing rocket science, we have to look at the force between the rocket and the Earth. Then we have to look at the force between the rocket and Venus, and the force between the rocket and Mars, and the force between the rocket and the sun, and the force between the rocket and Mercury, and all the other planets, and then we add them vectorially. And we would love to be able to do that just in one step. There's my challenge for you. There's a Nobel Prize, if you can solve it. 3 is good. You can skip 4, you can skip 5. 6 is good. 7 is good. 8 is good. 9 is good. 10 is good. And then I used to do circular motion as part of the gravitation unit, so it's obvious that number 11 and number 12 and number 13 are lovely reviews of circular motion, but I'm not going to be assigning those ones, I don't think. Okay? So I have assigned 1, 2, 3, 5, 6, 7, 8, 9, 10. 2 has some teeth. See if you can figure it out. Otherwise, I'll help you with it in Flex or next class.